Okay, in this example here, we're still given an ideal transformer, and we have turn ratio 4:1, but in this case we have some kind of line impedance and capacitance going on here, and then the load has got both a resistor and inductor. And as a side note here, if you tend to have a capacitive load, capacitive line impedance here, we want to have an inductive load. Just like conversely, if you have an inductive line impedance, you often want to have a capacitive load. And that comes from maximum power transfer. Remember, these capacitors and inductors give us that Q, those volt-amp reactive power. And we want to kind of cancel that out as much as possible for maximum power transfer. And so, if we have capacitive on the input, we would want inductive on the output. Now, I don't know if this is designed to be maximum power transfer, but I'm just saying that it's not uncommon to see a capacitor on your input and an inductor on the output because of trying to achieve maximum power transfer. All right, so let's go ahead and first draw our V1 and V2 and I1 and I2. And the V1, V2 is easy because it's just the plus goes with the dots. I1 goes into the dot. I2 comes out of the dot. And so my equations now I do know, and I'll even write them with the numbers in. I'll write some equations off to the side here. V1 over 4 is equal to V2 over 1. And that 4I1 is equal to I2. So I'll even kind of write this as equation 1 and equation 2 here. Okay. Well, we're asked to find what V out is. Now what I'm going to do here before we go through this is I'm going to kind of just combine these here into a single box because they're in series, and we know that components in series just add. So I can think this is just an 18 minus J4 ohm component. Similarly, on the load here, I can combine the inductor and resistor into a box and have it just be a 2 plus J. Let me draw the box a little bit better here. Let's draw it this way. There we go. A 2 plus J ohm component. It's J1, but yeah, just 2 plus J ohm component. And that just makes it so that the equations I'm going to write are going to be a little bit easier to write here, I think. So I'm of course trying to find V out. V out is the same as V2, of course. But I don't want to necessarily think about, okay, well, V out's V2. I mean, that's important here because that's how I'll get my final answer. But what I really need to do is I'm going to just have to draw loops here and write two loop equations here, because unlike in the previous example where we had the voltage source directly tied to the transformer, I have the voltage source and then some kind of line impedance tied to the transformer. So I have to take this into account, and the only way to take that into account is to be writing some loop equations. So this loop would be I1 and this loop would be I2. So we don't make this any more complicated than it needs to be. So if we light this for loop 1, we'd have minus 120 at an angle of 0 degrees is equal to 18 minus J4 times I1 plus, well, it's just going to be V1. And I'm sorry, that's not equal. There should be plus here. I don't know what I was doing. Got ahead of myself is what I was doing. Because then if I simplify this equation, I get 18 minus J4 I1 plus V1 equals 120. And I didn't write the angle 0 degrees because I'm just saying, well, I'll convert it to rectangular, which if I convert it to rectangular is just 120. All right, so this is another equation here. We can even call this equation 3. Because right here, these two equations, I've got two equations, but I have 4 unknowns in these. Now I got my second loop that I'm going to do, loop 2. And just going through that, that would just be 2 plus j I2 plus negative V2 is equal to 0. So again, nothing really complicated or shocking about that. We get loop equation that makes sense. Okay, and then we get here a fourth equation. So at this point, there are several ways we could go about solving these problems here. Okay, one way is to set up a system of equations right now. And to set up the system of equations here, I'm going to rewrite this equation up here as v1 over 4 minus v2 equals 0, 4i1 minus i2 equals 0. And so if I do that here, my 4 equations, if I wanted to think about them, I could have 0.25 v1 minus v2, and I'm going to put in some additional things here, plus 0i1 plus 0i2 equals 0. And then I could put in 0v1 plus 0v2 plus 4i1 minus I2 equals 0. And then I would have V1 plus 0V2 plus 18 minus J4 I1 plus 0I2 is equal to 120. And then finally I'd have 0V1 plus 2 plus j v2 plus 0i1 minus, I'm sorry, I got this wrong here. I flipped things up here. I wasn't looking carefully. I just didn't copy this equation. v2 is not plus that. It's got a negative there, so it's just minus v2. And then this would be plus 2 plus j I2 equals 0. And so I could literally use that calculator online or your calculator on your, the matrix calculator online or your calculator at home to solve this system of equations, and I'd get V1, V2, I1, and I2. And there's nothing wrong with doing that. The only thing is sometimes people think, oh, well, there's going to be more room for error. But there's always room for error in all of these steps. So it's really what you prefer doing. But another thing you can do instead is to do some substitutions here. And for instance, we can say here, if I look at this equation right here, I can say that V1 is equal to 4V2. And then if I look at this equation, I can say that I1 is equal to 0.25 I2. Now why do I do that? Well, I'm going to star this because then I could substitute that in to this equation right here. And then I'll put a little square here, and I could substitute that directly into here. So let's go ahead and do that and see what happens here. So I'm substituting into equation 3. So I have 18 minus J4. Now I1 is 0.25 I2. And then V1 is 4V2, and this is equal to 120. Then if I multiply things out here, just make sure I don't make a silly mistake multiplying, 4.5, yep. So I have 4.5 minus J I2 plus 4V2 is equal to 120. Now, I mean, that hasn't necessarily gotten me to solve the equation, but now if I look here, I have this equation and this one. And so I could set up a system of equations like the following. I could do 2 plus j I2 minus V2 equals 0. 4.5 minus j I1 plus 4V2 equals 0. And now I just have two equations and two unknowns to solve. So I could again use a matrix calculator. Now if you wanted to go even one step further, I'm not going to do this. If you really wanted to solve it completely by hand, you could just multiply this by then 4 and then add the two equations together. I'm sorry, there's a mistake here. This should be I2. And then add the equations together and figure out what I2 is. And then if you know what I2 is, you could figure out V2. But let's not do that. Instead, what I went ahead and did is I'm going to go ahead and I'm going to solve the simpler version equation here and write down what our answers are. And we get, of course, here, and I actually wrote a mistake here again. I think I said it correctly, but this should be equal to 120. But when I did this here on my calculator, if you use the online matrix calculator, sometimes it gives you the answer in fractional form, and so you have to divide it out. I find that kind of annoying, but I don't know why it does that sometimes. But I get 9.077 minus j 2.179 amps, and V2 is 20.33 plus J 4.72 volt. And of course, these are in RMS values. Now I'm going to go ahead and convert these to polar here. So if I convert them to polar, I'd get I2 is equal to 9.33 at an angle of negative 13.5 degrees amp RMS. And V2, which is the V out we're looking for, is 20.87 at an angle of 13.1 degrees volt RMS. Now, the reason I'm pointing this out here is, let's look at the magnitude of this voltage here. Because the mistake sometimes people make is that 120 and we've got a 4 to 1, so you're saying, oh, I'm dividing that by 40, so I should get 30 volts on the output. Because you take 120 down by 4, factor of 4, and you should get 30 on the output, right? Well, we didn't get 30 on the output, we got 20.87 or 21 on the output. So what's going on here? What did we do wrong? The answer is we did nothing wrong. The answer is that this voltage source here, this is not V1. And it's not the power supply that's connected that gets stepped down. It's the voltage that gets put into the transformer that gets stepped down. And because of this line impedance here, we're definitely going to have a voltage drop across this line impedance. So the thing that got stepped down was whatever V1 was. And of course we could find V1. We could find it just using the fact that it's 4 times bigger than V2. There's lots of ways we could find it. We could have found it if we had solved this system of equations, we would have found V1. But the point being that you don't want to always say, oh, it just steps the power supply down by that. It steps whatever is directly connected to the transformer. Now, when we think about plugging a wall outlet into a transformer, so if I got just a wall outlet here, and I'm thinking about plugging this into a transformer as part of my circuit here, we typically do just say, oh, well, I've got 120 plugged directly into a transformer, because as far as the circuit diagram often it goes, you know, this is what we would have for it. We would have my 120 from the outlet, and then we might have a fuse here. Because remember, we saw in one of the videos that some fusing might be required for a transformer. And then we just connect that directly into the transformer. And so what we'd really end up having is there'd be some kind of, well, we're assuming ideal transformers here. So we'd have our transformer here connected, just like that. And so when we're connecting directly from the wall, yeah, we typically don't have this line impedance. So you might say, well, why did I include an example with a line impedance if we typically don't have that? Well, that's when we plug directly into the wall. If you're talking about distribution systems, talking about power grids, talking about transmitting power, there is absolutely line impedance that you have to worry about. Because, you know, even though you might say, oh, wires have zero resistance or zero impedance, well, you're talking about wires that are really long now. So they are absolutely going to have some kind of impedance that can actually have a significant impact on the answer, as we can see it did in this case here. All right, so that actually wraps up material for the course here. So make sure to look at the homework and the solutions and get all of your assignments completed. All right, I hope you've enjoyed this course. Hope you've learned a lot of things from here. And you'll be progressing on at this point. This is kind of fundamentals here. These first two courses, it's fundamentals of circuit analysis. You'll really start diving into applications more in your future courses. There was one more introductory course on digital logic, and then you'll start diving into things like PLCs, programmable logic controls. You'll actually talk about machines like generators and things of that thing, motors. So, you know, after this is kind of when we really start diving into the applications.